All right, so let's talk a little bit about the differences between a DAG protocol and a standard blockchain. I think it's important for people to understand, what are some of the key differences and challenges, and frankly, upsides to the DAG protocol. And we'll also, I think, want to explore some of the innovative ways that we've, been able to solve some of the challenges of involved with using a DAG protocol. So maybe you could just start, Price, with an explanation of like, okay, just give us the 10,000 foot view level of like the difference between a DAG and a blockchain.
I think that that one of the underappreciated benefits of a blockchain that was achieved in the architecture of using sequential blocks is that you have a known state of the network, even though the network consists of completely distributed, unreliable nodes operating all around the world. If you are operating a node on a blockchain like Bitcoin, your view of the blockchain after some number of blocks, like 4 or 6 blocks old, your view of the blockchain is identical to every other participant on the network, right? With the exception of the mempool, which we can get into in a second. On a DAG, there are no sequential blocks. There's no kind of network heartbeat. There's no network clock that's kind of keeping everything organized so that you could look back to any point in time and know that your view of the transactions on the DAG is an exact match of every other person's view of the DAG from that same point. The blockchain was an amazing achievement, and a known state of the network is one of the reasons why it's as important and valuable to society as it's become. The cost, the downside of that architecture is that you can only send as many transactions per second on the network as you can fit into a block. And so the size of the block, how many transactions can fit inside each block, and the time duration between each block is kind of the definition of your ceiling. And projects like Bitcoin, in I suppose it was 2018, there was a inter-community battle about increasing the size of the blocks from 1 megabyte worth of transactions to some larger number. And the Bitcoin community held fast on 1 megabyte as a block size, and that kind of continued the maximum number of transactions per second that Bitcoin could achieve. DAGs, by getting away from the concept of blocks and just allowing transactions to flow from sender to recipient through other nodes, kind of in real time, the benefit of that is tremendous scale in speed and data storage. The problem that we realized was that you couldn't just have transactions flowing from sender to recipient in kind of this chaotic fashion without using centralized controllers or validators that could be used to kind of simulate a known state of the network. If every transaction has to flow through some number of nodes that are trusted not to be bad actors, if you don't do that, then not only does everyone's view of the network at a given point in time vary from node to node, but the data stored in a DAG for each transaction that indicates whether it's spent or whether it's a double spend, that information can change over time. And not necessarily just over a short period of time, it can be years, right? And so you're faced with a problem with a DAG where to achieve a known state of the network, you either introduce centralization and choke points, or you have to constantly inspect and re-inspect every transaction that's ever occurred, looking for changes all the way back to Genesis.
Right, right. And in both of those scenarios, as the network grows, both the centralization will increase in the amount of, the ability for the network to scale becomes hampered by just the amount of traffic that's happening on that network and the amount of gossiping from one node to another about current state and transactions and everything else. So that's the kind of the network in effect, but working against against the interests of the overall network, right? So how do you solve for that, right? In the traditional DAG, you just have to centralize things.
You either have to kind of not taking into account the solution that we came up with, but before we get to that, when you talk about that chatter and the network going back and forth, trying to keep everything in sync, that's introducing a large load on the network, and that large load isn't offset with any level of certainty. You're still not able to achieve a known state of the network, even if you're flooding the network with signals. And so that's one problem. The other problem is that, which is somewhat similar, if you're using centralized controllers and validators to flow every transaction through on the network, you've realized a choke point in the throughput of the network from transactions per second. And you can't just add more of those centralized controllers or validators to gain scale. Because as you add more of them, now you're introducing that network chatter between those. And so you're adding load when you're trying to reduce load.
Right. It's just exacerbating the problem.
It didn't seem to work.
Yeah. So then what did we do to solve that problem? What was the aha moment or the discovery that the team came up with?
Yeah, well, before the aha moment, there was an uh-oh moment. And the uh-oh moment happened when we started the first layer 2 implementation on top of the Millix network. And the uh-oh moment was the realization that since we had really aggressively stayed away from centralized controllers or centralization of any kind, we didn't want any node to have we didn't want a hierarchy of nodes. We didn't want any special permissions or privileges or functions that one node could have that another node could not have. And so we realized as we were starting to do a layer 2 implementation that you would have to, like, for example, to power an Explorer, where you can look up the balance of an address or look at a historical transaction and kind of prove that you sent something to someone and they use that. And you can look at the attributes of a node. It's really a good user interface into the network. And in building that, we realized that we were going to have to analyze every single transaction that occurred between any nodes on the network and reanalyze them frequently forever. And so every single time a new network happened, a new transaction happened on the network, the job that we would have had to do got bigger and bigger until you get to the point where in our minds, the exaggerated statement was we need all the energy of the known universe to be able to make this thing work. All right, so that was the uh-oh moment.
So in that scenario, success would look like failure because the network would just grind to a halt or would require so much investment in hardware and energy that it would just be untenable, right?
Exactly that. So we got together as a team to try to understand the problem and see if we could find a solution. And it was Dr. Emmanuel Braden, who's a co-founder of Millix. He kind of flippantly said, well, all it would just be nice. All we need is for transactions to freeze after some point in time and not be able to be changed with information about whether they've been spent or double spent or whatever. And that set us on the path to the solution that we think is kind of It's innovative, and I think that it's the best of a blockchain and the best of a DAG combined in a way that I don't think has been done yet.
Okay, so lay it on me. What was this innovation? What was this discovery?
Yeah, so we thought that after some arbitrary amount of time, and we kind of settled on 10 minutes, uh, every transaction on the network enters into a state of hibernation. And a hibernated transaction no longer changes. Even if something is discovered about that transaction, in the meantime, when it's hibernated, it doesn't change. And it also can't be used in the normal way. If you have received a payment, once that payment is more than 10 minutes old, it can't be used and sent on to someone else in the normal way. It's hibernating. And so in order to use that hibernating transaction, when you want to spend that money sometime in the future, and you send a transaction, say I'm going to send a transaction to Rick. In the background, the protocol is going to take that hibernated transaction, and it has a special transaction type, which kind of makes it subject to a kind of a different set of rules than a normal transaction. It sends the money to myself, right? So it's creating a new transaction funded by the hibernating transaction, and the network revalidates that refresh transaction like any other transaction. It's looking for double spends, it's looking for compliance with all the rules. And this happens very quickly. So that refresh transaction happens, the money comes back into my account in a brand new non-hibernating transaction, and then the system uses that to fund the transaction that I'm sending to Ray.
Interesting. So basically, if I understood that correctly, so I have my funds, and after 10 minutes, and then beyond in the future, all those funds are hibernated basically, and then I want to spend them, and as soon as I attempt to send them to another destination, the network is going to effectively wake up the funds, right, that need to be spent. And by activating them or waking them up and spending them back to myself, now they're ready to be sent or spent, I should say. And that kind of gives, I guess, in a way, that gives the network every 10 minutes. There's this you've snapped a virtual chalk line, and you've set like a stake in the ground, if you will, of like, okay, here's the known state of the network, and there's a sense of finality, I guess, of those transactions.
Yeah.
There's a known state, in other words, right? And it's like, okay, got it. Now, we just have to remember, the rest of the nodes only need to know about and talk about what's happening right now and for the next 10 minutes. Is that a fair summary?
Correct.
Okay, great.
Yeah, and the key point in that is that it doesn't matter what has happened related to that hibernated transaction in the meantime, because it's going to be because it can't be used on the network until it's revalidated again using all the information that the network has that's happened since that hibernation started. Yeah, and that 10-minute kind of clock to establish a known state of the network is a rolling 10 minutes. It's not 10 minute, 10 minute, 10 minute like a blockchain. It's always rolling. And 10 minutes, the 10-minute time, like I said, it's a bit arbitrary, but it's a good amount of time for information about a new transaction to propagate through all the nodes and for double spends to be detected right away. And the amount of time, 10 minutes, kind of determines the computing power that's needed for a device to keep up with the network. If it was longer than 10 minutes, a device would have to work harder. And if it was shorter than 10 minutes, a device wouldn't have to work as hard. And there's trade-offs there, and we settled on 10 minutes for that.
Okay, so
And by the way, let me just say that the things that we're talking about don't have anything to do with how double spends are detected or prevented. It doesn't have anything to do with the certainty that you get from a validated transaction. This is a feature I think that's most valued by layer 2 developers. So exchanges, um, any developer that wants to build anything on top of the millix network, this is a godsend for them. As we found out when we were trying to implement our own layer 2 implementation on top of millix.
is that because, well, you say it's a godsend for any layer two developers, any exchanges that want to trade in Millix, and that's because why they wouldn't need to invest so much to kind of build, test, and production networks, because they wouldn't have to, and by invest I mean they wouldn't need this massive amount of hardware and computing power and storage, right? To be able to effectively test.
Yeah, it's it's because if you're running a layer 2 application like an exchange or an explorer, and some of the if you're running an exchange, some of the transactions that happen on the network are really important to you. Your customers' deposits, those are really important to you. And then there's every other transaction that's not as important. When you're building an explorer, every transaction is equally important. And if we're not hibernating and freezing the state of a transaction, in order to have kind of current state of the network, you have to continually reevaluate every transaction that's ever happened. And what that means is, if you're an exchange, you're running some servers, your servers are going to have to make an API call to a node operated on the millix network all the time and say, give me a list of transactions or give me information about this specific transaction for every transaction forever.
And so,
that's the hardware problem.
so I'm going to say something, and I'm not sure if it's correct, but it almost feels like what you're describing is, in a way, Millix is almost like a self-pruning protocol, right? Because the nodes only need to worry about what's happening right now and for the a rolling 10-minute period, and everything else behind it is behind it, and we don't have to keep validating and confirming all of the known transactions back to Genesis. Is that?
That's a great way to put it. Yeah. And kind of the consequence of that is that you want to have on your node, you want to have all the transactions that are important to you. You want to save them, you want to back them up. Because for all you know, you're the only node that has them. You don't know what other nodes are pruning off, because, as you say, they could. And if they did, it makes millix that much more efficient. You're no longer looking at a billion or a trillion transactions. You're looking at 10 minutes worth of transactions to know what's going on. Because everything that happened before that is irrelevant until it's used. And when it's used, it's going to be reintroduced to the network as a brand new transaction to be inspected.
Okay, got it.
It's almost like on the Bitcoin blockchain, you've got a stack of blocks that contain transactions from that period of time, and every transaction that's waiting to be put into a block is sitting in this thing called the mempool, which is kind of a chaotic place. No one has the same view of what's contained in the mempool. It's different all over the place. That the 10-minute time period in millix prior to hibernation is similar to the Bitcoin mempool. The exception is that you don't have to necessarily store the entire equivalent of a blockchain all the way back to Genesis block to be able to participate and validate transactions, because those historical transactions that get spent are going to be reintroduced for you to analyze all over again. You just when they're reintroduced to be validated, you just need to have access from the history behind those transactions from somewhere. And that's why it's prudent to have a copy of all the transactions that are important to you, payments you've received, payments that you've sent, back up the database, your millix or your Tangle database on your machine, so that you're certain that the history of your transactions are available somewhere for the rest of the network to use to validate whatever you do with the money next.
Great. So, I mean, what I'm hearing is, this feels like millix represents, it's built on the DAG protocol, invented by this team. And it really represents the best of DAG, which is, a lot of speed and scalability, throughput, enormous upside on all of those fronts, with a little bit of kind of what's great about a blockchain, which is that like snapshot, in our case, kind of a rolling, snapshot, but gives that sense of like network finality and known state of all transactions. Which prevents millix protocol from having to, centralized nodes or special tiers of nodes that are like the granddaddies that do all the, that hold the entire history of what's happened on this network. And as the network grows and becomes more successful, they have to get larger and larger and more intensive in terms of computing power and storage and energy costs and everything else. All of that is gone, right? Because of this innovation. And we're able to keep every node at a, quite frankly, a very minimal footprint. I mean, effectively, a browser, with millix, a millix node running in the browser itself is all it takes, right, to be a full participant in the millix network. So, I mean, it's really incredible when I think about it that way. And, maybe I feel like maybe I only touched on a couple of, the key upsides or benefits. If I've missed something, chime in with, what else, that you think that is a key outcome from this innovation.
Yeah, everything you said is right. And what blockchains, the innovation of a blockchain was a distributed ledger. To use your phrase, that could solve the world, right? But you can't have a distributed ledger without every participant agreeing on what's in that ledger at some point in time. And the cost of that is speed and scale. And the DAG solves the problem of speed and scale, but it didn't have a great solution for a state of the network. And when we kind of came up with this innovation, it was, the immediate feeling was relief, just that we could continue to build and meet all of our objectives without having this big problem. But as we started to live with the solution and kind of step back from the solution a little bit, that relief started to turn into a sense that maybe we had just solved something really, really important. And that by merging a really important attribute of a blockchain with a really important attribute of a DAG, that we had really come up with something that might be the best of both and useful for everything.
And I think the one key thing that occurs to me here is that this is all done at layer one of the protocol, right? I mean, there's no like, oh yeah, well, we'll build on top of this and create some sort of layer two solution for, that'll give us scale and speed. No, this is all like, please tell me I'm wrong if I've got it wrong, but what I'm understanding is that this is all layer one protocol.
Yeah, and it would have been easier to figure out a layer two solution. The problem would have been that once you get above layer one, when you get into layer two and layer three, you start to introduce inconsistency in the problem solving, and this was a core fundamental problem that we felt we had to solve in layer one, that every single user and every layer two developer would benefit from.
Yeah, I mean, it's just, it's really exciting and a phenomenal, solution that the team came up with. Let's see if it, I can't wait to see what the rest of the world thinks. Maybe we have discovered and innovated something here that will really kind of change, the world in effect.
That's it. I hope so.
All right. Well, I'll catch you on the next, segment about going deep on aspects about Millix Entangled. Thanks a lot, Price.
Thanks, Rick.